What if the emptiest thing in the universe is not truly empty at all? What if the vast black space between stars, planets, and galaxies is hiding something far stranger than anyone ever imagined tonight? This journey goes deep into one of the most unsettling mysteries in science. Because nothing may not be nothing, it may have structure, energy, and a hidden role in shaping the universe itself. Before we begin, please take a moment to like the video, subscribe to the channel, and share it with anyone who loves cosmic mysteries and science documentaries. Thank you so much for being here and for spending this time with the channel. It is always amazing to have curious minds from around the world joining in. And as always, feel free to leave a comment sharing what time it is where this is being heard and which part of the world is listening tonight. Now, with that said, let us step into the silence of the cosmos and begin. Long before telescopes sharpen the sky and long before mathematics begins to bend space into strange new forms, one fact waits in plain sight. Night falls, the stars appear, and darkness remains. The human mind notices the stars first because they shine, because they puncture the black with points of cold fire, because they suggest distance and order and perhaps a hidden design. But the deeper fact is not the presence of light. It is the survival of darkness. In a universe that seems crowded with suns, darkness should be fragile. It should be overwhelmed. It should fail. Yet it endures, spreading between stars, between galaxies, between every known structure in the cosmos, as though emptiness itself has a claim on reality stronger than matter, stronger than fire, stronger even than time. This is where the story begins, not with an object, but with an absence that may not be an absence at all. Seen from Earth, the night sky looks rich. On a clear moonless night, the Milky Way stretches overhead as a pale river of unresolved light. Ancient observers see patterns there. Animals, hunters, monsters, royal figures, stories fixed against the dark. Later observers see something stranger. They begin to understand that each point is not a hole in a ceiling or a jewel attached to a sphere, but a distant sun. Then scale begins to widen with unsettling speed. The sun, which dominates the days of Earth, becomes one ordinary star among hundreds of billions in the Milky Way alone. The Milky Way then becomes one galaxy among perhaps hundreds of billions more across the observable universe. Modern surveys from NASA, ESA, the Hubble Space Telescope, the James Webb Space Telescope, and large ground observatories all strengthen the same picture. The universe is not sparsely lit. It is crowded beyond easy imagination. There are stars being born in nebulae, stars burning steadily for billions of years, stars collapsing, stars colliding, stars dying in explosions bright enough to outshine whole galaxies for a short time. There are so many luminous objects that any simple picture of a mostly empty cosmos begins to feel misleading. And still the sky is dark. That contradiction sits quietly behind almost every other astronomical discovery. It is easy to miss because familiarity disguises it. Darkness seems natural to creatures that live on a rotating planet. Day belongs to the sun, night belongs to its absence. That sounds complete, but it is only local. The planet turns, the sun slips below the horizon, and darkness returns. Yet the horizon is not a wall. Beyond it lies the rest of space, filled with stars in every direction. If the universe is large enough, old enough, and populated enough, then every line of sight should eventually end on a star, just as every glance in a dense forest ends on a trunk. The sky should not look like black velvet scattered with sparks. It should look like a continuous blaze. It should be washed in light so thorough that night never fully arrives. The darkness above Earth should be only a temporary illusion caused by the loss of one nearby star, not a profound feature of the cosmos itself. This is the first crack in common sense. The sky appears simple, but it behaves like a riddle. Every visible star seems to testify that light is abundant. Every dark gap between stars seems to argue the opposite. The contradiction grows sharper as knowledge grows sharper. Once the Milky Way is recognized as a vast disk of stars, the darkness becomes harder to excuse. Once Andromeda is recognized as another galaxy, the problem deepens. Once astronomers find that there are galaxies beyond galaxies, arranged in clusters and filaments across incomprehensible distances, darkness begins to look almost impossible. The more the universe reveals its contents, the less natural its blackness seems. At a glance, empty space appears passive, just the interval between real things. But the night sky suggests something more troubling. It suggests that emptiness may not merely separate light, it may govern it. Early science does not solve this at once because early science is still deciding what space is. Is it a container, a stage, a silent volume where matter drifts, or does it have properties of its own, even before the great revolutions of modern physics? This question hides inside simple acts of looking upward. The stars seem embedded in depth, but depth itself is hard to define when nothing marks its boundaries. The eye sees distances only by comparing objects. Remove the objects and what remains is hard to grasp. A gap between two lamps can be pictured. A gap between galaxies can be measured. But what is the reality of a gap where no lamp, no galaxy, no atom, perhaps nothing at all is present? The ordinary word space suggests room, openness, extension. Yet the darkness of the cosmos begins to whisper that space may be more than room. It may behave, it may filter, it may stretch, it may conceal. It may even create conditions under which light, despite its speed and abundance, never fully conquers the void. The strange power of this idea lies in how modestly it enters the story. No violent event is required. No exotic object is required. Nothing dramatic needs to happen except sunset. A child lying awake under a clear sky can notice the same thing that later troubles astronomers and cosmologists. The universe above looks full, but not full enough. It looks active, yet mostly silent. It suggests endlessness, but it withholds itself. The visible stars provoke wonder, while the black between them provokes something else, a gentler but deeper unease. The black does not look accidental, it looks structural. It looks as though reality is built not only from object but from absence, and that the absence has rules. As telescopes grow more powerful, this unease deepens instead of fading. A larger telescope does not merely reveal more stars, it reveals that more stars lie behind those stars, and more galaxies behind those galaxies. The darkness retreats under magnification, but never disappears. It is always waiting at the next scale. Images from deep field observations make this especially clear. A tiny patch of sky that once appears empty becomes crowded with thousands of galaxies when exposed for long enough. Each galaxy contains immense numbers of stars, yet even then the image is not flooded into uniform brightness. The dark remains threaded through everything. The universe seems willing to fill every improved instrument with more structure, more matter, more light, and still not enough to erase its own background. This persistence begins to feel like evidence, not evidence that the universe is mostly nothing, but evidence that what looks like nothing is doing something essential. That suspicion grows stronger when time enters the problem. Light does not arrive instantly. Every glimpse of the sky is also a glimpse into history. A nearby star is seen as it was years ago. A distant galaxy is seen as it was millions or billions of years ago. The night sky is not a map of simultaneous objects. It is a layered archive of delayed light. That means darkness may not simply be the absence of stars in certain directions. It may be the absence of enough time for light to arrive from farther regions. It may be the mark of a universe with a beginning, or at least with a visible limit. Yet this explanation, powerful as it becomes, does not empty the mystery. It changes its shape. If darkness exists because light has not yet had time to cross the whole cosmos, then emptiness is bound to time itself. The void is not just where nothing is. It is where history has not yet delivered its signal. It becomes less like blankness and more like a frontier. And beyond that frontier, imagination begins to stir, not wild fantasy, but disciplined speculation anchored to what the sky actually does. If darkness depends on the age of the universe, then the black above Earth is evidence of a cosmic past. If it depends on expansion, then emptiness is not still but growing. If space can stretch, then the void is not passive distance but an active participant in the shape of reality. Later physics will push even further, suggesting that empty space may teem with fleeting quantum activity, with fields that cannot be switched off, with energies too subtle to notice directly and too powerful to ignore forever. But all of that comes later. At the beginning, there's only the oldest clue of all, a sky full of stars and not enough light. The universe offers abundance and withholds illumination. It reveals brilliance, but preserves shadow. In that balance between radiance and blackness, a deeper possibility begins to emerge. Perhaps nothing is not the opposite of everything. Perhaps it is the hidden condition that allows everything to appear at all. For centuries, the sky appears fixed not because anyone proves it is fixed, but because it behaves with such disciplined repetition that stability seems unavoidable. The stars rise and set in orderly procession. The familiar constellations return with the seasons. The planets wander, but the deeper background seems almost immune to change. In the old cosmology inherited through antiquity and refined across medieval Europe, the Earth sits within a layered universe, enclosed by crystalline or near-crystalline spheres, each carrying its appointed lights. Beyond the moon lie the planets, beyond the planets the fixed stars, and beyond the stars perhaps the outer boundary of creation itself. In such a picture, change belongs mainly to the lower world. Storms gather, bodies decay, kingdoms rise and fall, but the heavens remain incorruptible. The upper realm is not merely distant, it is supposed to be perfect. That confidence survives because the sky usually rewards it. A human life is short enough that slow celestial changes pass almost unnoticed. A star that burns steadily for centuries encourages the illusion of permanence. The heavens seem less like a place where events happen than a structure already completed. The black between the stars looks deep, but not unstable. It looks ancient, but not active. Even mystery is given boundaries. There are things not understood, but they unfold inside an architecture that seems secure. Then, in the late 16th century, one new light appears where no new light should ever appear, and the confidence of ages begins to tremble. In the year 1572, observers across Europe notice a brilliant object in the constellation Cassiopeia. At first it looks like a bright new star. Soon it becomes impossible to ignore. It shines with a force that rivals the brightest known planets, and, for a time, can be seen even in daylight. The event is now understood as a supernova, the catastrophic death of a star, one of the most violent natural processes in the cosmos. At the time, almost no one possesses a framework capable of explaining it in those terms. The phenomenon arrives before the language required to contain it. It appears suddenly in a sky believed to be complete. It changes brightness over weeks and months. Then it slowly fades. Its very existence seems to violate the rules of the universe as many learned people understand them. The shock is not only scientific, it is cultural, religious, even psychological. A sky that has long served as the emblem of constancy has admitted intrusion. The event invites omen, prophecy, fear, argument. Some interpret it within sacred history. Some treat it as an atmospheric disturbance. Some suspect a miracle. Some a warning. Some a sign still too obscure to name. But beneath all interpretation lies a simpler disturbance. If the heavens can generate a new light, then perhaps the heavens are not fixed. If one star can appear where none existed before, then perhaps the sky is not a finished design, but a changing environment. That possibility does not arrive all at once. It spreads slowly, like a crack moving through glass. Among the figures drawn into this uncertainty are careful observers who begin to ask a question more radical than the event itself. Not what does this light mean, but where is it? This is the quiet revolution concealed inside the spectacle. Meaning can remain symbolic. Location cannot. If the new star lies close to Earth, perhaps in the atmosphere, then the old celestial order may survive. But if it lies among the stars themselves, then the supposedly incorruptible heavens have changed in full view of humankind. That is a far more serious disturbance, because it does not merely decorate the old picture with a marvel, it breaks the frame. Tycho Brahe studies the object with unusual precision and finds no measurable parallax large enough to place it near Earth. Its position does not shift as a nearby atmospheric object should. It appears to belong to the distant celestial realm. The conclusion is devastating to inherited certainty. Something in the region of the fixed stars has altered. A new light has emerged in the very domain that is meant to be beyond decay and generation. The sky has not only surprised its observers, it has contradicted the philosophy built upon it. This is the moment when the heavens cease to be merely overhead and begin to become a problem. The stars are still beautiful, still remote, still apparently ordered, but now they carry an instability that cannot be forgotten. Once one impossibility has happened, every other assumption becomes vulnerable. The shell of fixed stars no longer feels like a final answer. It begins to look like a convenient appearance, a pattern mistaken for structure. The eye still sees a dome. The mind begins to suspect depth. In England, Thomas Digges is among those affected by this shift in understanding. He belongs to a generation living in the afterglow of Copernicus, when the placement of Earth itself is already under challenge. If Earth is no longer the unmoving centre, then location in the universe has become negotiable. The supernova pushes further. If the stars themselves are not fixed in unchanging perfection, then even the architecture of the cosmos may need rebuilding. Digges is not working with modern instruments or modern physics. He is working with a transformed sense of possibility. That is often how revolutions begin in science. The data do not yet provide the whole answer, but they make the old answer impossible to keep. The power of the event lies partly in how brief it is. Had the light remained forever, it might have been absorbed as a permanent addition, folded into the old sky as though it had always belonged there. Instead, it fades. It arrives, dominates, diminishes, disappears. The heavens are shown to contain a kind of temporality previously reserved for earthly things. Something has happened above, and then it has passed. This introduces a subtle new form of dread into the study of the universe. If celestial objects can appear and vanish, then perhaps the sky has a history. If it has a history, then the visible order overhead may be only a moment in a much larger process. The cosmos begins to feel less like a monument and more like an unfolding. That shift in feeling matters because astronomy is never guided by observation alone. It is guided by expectation. A mind that expects perfection sees anomaly as error or omen. a mind that allows change begins to search for process. In this sense, the supernova of 1572 does more than add one object to the record. It changes what future observers are prepared to believe. It weakens the boundary between earth and heaven. It turns the sky from a symbol into a field of events. It opens a dangerous line of thought. If the stars can change, perhaps they can be born, move, die. If the heavens are not sealed, perhaps space is not enclosed. If the dark above is not the inside of a cosmic shell, perhaps it extends far beyond what the eye suggests. This is where speculation begins to slip naturally out of evidence. Not reckless speculation, but the kind that grows from a broken certainty. The old dome of stars depends on visual intuition. The new doubt depends on one intrusion of light. Yet that single intrusion changes the scale of every question. A shell can be mapped, an open depth cannot. A perfect sky can be described. A changing sky must be investigated. The darkness between the stars, which once seems like the inner surface of a boundary, begins to feel more like a hint of immeasurable distance. The stars may not be attached to anything. They may occupy a vastness with no obvious edge. The blackness around them may not be the wall of the universe. It may be the universe. That possibility is still almost unbearable in the late 16th century. Infinite space is not yet a comfortable scientific concept. It is philosophically destabilizing, spiritually unnerving, and observationally unsupported in any complete way. But the supernova has done its work. It has shown that the heavens are not immune to surprise. Once surprise is admitted into the sky, there is no easy way to prevent it from spreading. The old structure remains in books and lectures, but it now carries a wound. In the years that follow, the mind turns upward with a new unease. The stars are no longer merely fixed lights. They are clues. The darkness between them is no longer empty decoration. It is a question waiting to widen. One vanishing star has altered the character of the universe. The sky still looks calm. Beneath that calm, certainty is already receding. Thomas Digges inherits a sky that has already begun to loosen from its ancient frame. Copernicus has displaced Earth from the centre. The new star of 1572 has shown that the heavens can change, and yet much of the old structure still survives in modified form. The sun may now stand nearer the centre of the known system, with planets moving around it, but the stars often remain where tradition leaves them, fixed upon a distant outer shell. This compromise is powerful because it preserves familiarity. It allows a new arrangement of the nearby heavens while protecting the deeper background from collapse. The planets may move differently than once believed, but the universe as a whole can still feel contained. It can still have an outer skin. It can still possess a final boundary where visible reality comes to rest. Digges is one of the thinkers who begins to suspect that this compromise cannot last. What changes in his imagination is not simply the placement of stars, but the meaning of appearance itself. A night sky naturally suggests enclosure. The stars seem to arch over the observer like points on the inside of a globe. The illusion is almost irresistible because human sight is poor at judging vast distance without intermediate markers. A row of lamps on a distant shore can look like a single flat band until movement reveals depth. The sky behaves in much the same way. The stars seem equally remote because the eye has no scale large enough to compare them. That apparent uniformity encourages the idea of a shell. Digges begins to see that the shell may be nothing more than the mind mistaking perspective for structure. When he publishes his famous diagram in the later 1670s, attached to an English account of the Copernican system, the image looks deceptively simple. On one side stands the older arrangement, with planetary orbits centered on the sun and the fixed stars circling at the edge. On the other side, Digges keeps the planetary order but tears away the final stellar boundary. The stars no longer belong to a containing sphere. They are distributed outward into an endless depth. What had seemed a wall becomes an abyss. What had seemed a ceiling becomes distance. The universe does not end where the eye ceases to resolve it. It continues. This is one of the most profound shifts in the history of human thought because it changes not only astronomy, but psychological scale. A bounded universe can be pictured. An unbounded universe resists ordinary intuition. In the older world, everything exists inside a cosmic architecture. Place and purpose feel linked because every layer has an assigned role. In Diggis's universe, that security weakens. The stars are no longer the decorations of an outer dome. They are bodies suspended in depth without obvious limit. Earth is not merely displaced from the centre, it is immersed in a vastness with no visible edge. The darkness overhead is no longer the surface of the last sphere. It is open space, extending beyond every known light. This proposal is bold, but it does not arrive with proof in the modern sense. No one in Diggis's time can measure interstellar distances with precision. No one can show the structure of the Milky Way. No one can count galaxies. His leap is partly philosophical, partly observational, and partly the consequence of old certainty becoming too fragile to hold. Yet it carries an uncanny power, because it explains something the shell cannot explain: the impression of immeasurable depth. Once the mind releases the fixed sphere, the stars begin to look less like a pattern painted on a surface, and more like scattered presences in a vast unseen medium. The black between them acquires volume. The sky stops being a cover and starts becoming a region. But the moment this infinite vision appears, it generates a contradiction as severe as the one it solves. If the stars are distributed through endless space, then how can darkness remain? The problem does not need advanced mathematics to become disturbing. Every direction in the sky contains stars. If space goes on forever, and the stellar population also extends without limit, then every line of sight should eventually encounter a star or the surface of one. Near stars might be sparse, but more distant stars would compensate by existing in greater numbers. The farther one looks, the larger the shell of space under consideration becomes, and the more stars it ought to contain. The light from those distant stars might individually be faint, but there should be so many of them that together they fill the sky. The whole firmament should glow. This is the heart of the paradox that later generations associate with Heinrich Olbers, though its roots reach back to Diggis and beyond. A static, infinite universe full of stars should not possess night. It should present a luminous background in every direction, comparable in surface brightness to the face of a star. The darkness familiar to every human observer should be impossible. The argument is so simple that it seems almost like a trick, yet it cuts deeply because it turns ordinary experience into a refutation of careless infinity. Endless space alone is not enough. A universe cannot simply be declared infinite and then left unchanged. It must also account for the blackness between the stars. At first glance, there seem to be easy escapes. Perhaps interstellar dust blocks the light. Perhaps matter in space absorbs the radiation before it reaches Earth. But this only postpones the problem. Dust that absorbs starlight would heat up and eventually radiate energy back out. Given enough time in a static, eternal universe, even the absorbing material would begin to glow. The darkness would once again vanish. Another possibility is that stars have not existed forever. Yet this already begins to undermine the old image of a static, timeless cosmos. To preserve darkness, time itself must enter the structure of the answer. That is the deeper importance of the paradox. It turns a question about vision into a question about the history of reality. Why is the sky dark at night becomes inseparable from larger questions. Is the universe finite or infinite? Has it existed forever or did it begin? Are the stars eternal or temporary? Is space static or changing? What looks like a simple observational fact begins to press against the largest possible issues. Darkness is no longer merely the absence of daylight. It becomes evidence. It becomes a clue that the universe may not be arranged in the way intuition first suggests. The paradox also alters the emotional tone of cosmic thought. Diggers opens the universe into endlessness, which at first feels liberating. The stars are freed from their shell. Space becomes grander than any enclosing system. But the darkness forces a second movement. Infinity no longer feels like an answer. It becomes a hazard. If one says the universe is endless, one must explain why endlessness does not shine. The black sky above Earth begins to operate like a quiet contradiction within every grand idea. It allows expansion of imagination, but refuses lazy conclusions. It accepts wonder and demands discipline. This tension between expansion and restraint defines much of the scientific journey that follows. Telescopes improve, more stars appear, nebulae complicate the picture, distances stretch, the known universe grows by repeated acts of enlargement, yet the darkness remains as a corrective. It says, in effect, that size alone explains nothing. A vast universe can still fail to fill the sky with light. Something about time, structure, motion, or the nature of space itself is limiting what can be seen. The paradox is therefore not a minor footnote to the story of astronomy. It is one of the first signs that reality may be more dynamic, more contingent, and more peculiar than either ancient cosmology or early modern speculation can yet express. And there is another strange implication resting beneath the logical one. If darkness survives in a universe full of stars, then emptiness has a kind of authority. The void cannot be dismissed as a leftover interval between luminous things. It exerts influence, whether by distance, by expansion, by the delayed travel of light, or by some deeper property not yet understood. The dark sky is not merely what remains after stars are subtracted. It is the visible form of a hidden rule. It tells observers that the universe withholds itself. Not all light arrives. Not all regions are accessible. Not all of existence stands revealed at once, or perhaps even in principle. From the moment Diggers transforms the stellar shell into endless space, the black above becomes more than background. It becomes an active mystery, a sign that what looks empty may shape what can be known. This is why the infinite universe of the late 16th century feels both exhilarating and unstable. It enlarges the cosmos beyond any inherited boundary, yet immediately collides with the simplest experience of night. It offers freedom from the old celestial prison, yet replaces that prison with a deeper uncertainty. The stars are now scattered through immeasurable space, but the space does not behave transparently. It does not simply transmit all light from all directions. It preserves darkness with stubborn fidelity. The result is a new intellectual atmosphere, one in which every advance opens another wound in understanding. The sky is no longer a completed order waiting to be described. It is a layered problem, vast enough to absorb imagination and disciplined enough to punish it. Diggers does not solve that problem. He makes it unavoidable. Once the shell breaks, the universe becomes larger than vision, and the darkness becomes harder than ever to explain. By the end of the 18th century, the universe remains unsettled but still largely unreachable. The shell of fixed stars has been broken in thought, yet thought alone cannot measure the new abyss. The mind can imagine endless depth, but the eye still confronts a sky of unresolved lights. The stars may no longer belong to a crystalline boundary, but they are still too distant to reveal their true arrangement. Even the Milky Way, that faint band clouding the darkness, remains ambiguous. Is it a local concentration of stars, a ring around the sun, a vast system with shape and edge, or only the brightest visible portion of something even larger and more diffuse? The old certainties have been weakened, but no new map has yet replaced them. The universe has become a question without scale. This begins to change in a modest house in Bath, where William Herschel and his sister Caroline Herschel turn craftsmanship into a form of cosmic exploration. Their work does not begin with grand theory. It begins with metal, heat, polish, and patience. Mirrors are cast, ground, shaped, and refined by hand until they can gather more light than the refracting telescopes that dominate much of earlier astronomy. This is one of the quiet truths of the scientific story of the cosmos. Before the universe can be reimagined, it must first be made brighter. It must be coaxed into visibility by instruments capable of holding more of its faint signals. The darkness between the stars is not only a philosophical problem, it is also a technical one. Much of space appears empty simply because human eyes and early lenses fail to collect what is there. William Herschel arrives in England as a musician, not as an established astronomer. That fact matters because it reflects the unusual route by which some of the greatest discoveries emerge. He approaches the sky with an outsider's hunger and a craftsman's persistence. Caroline, often reduced in popular memory to the role of assistant, is in truth an indispensable observer and collaborator. Together they transform long nights into a disciplined harvest of light. They scan, record, compare, and classify. They work under cold skies with instruments they have often built themselves. The labour is physical, repetitive, and exhausting. It is also revolutionary. Each improved mirror deepens the visible universe. Each new observation chips away at inherited appearances. With these telescopes, Herschel discovers Uranus, a finding that instantly expands the known solar system and confirms that the heavens still contain surprises on scales both near and far. Yet the deeper consequence of his work lies elsewhere. He begins to carry out systematic star counts, using the density of stars in different directions to infer the broad shape of the stellar system to which the Sun belongs. The reasoning is simple, but bold. If stars fill space more or less uniformly, then directions with more stars may indicate greater depth of the system in that direction. From this method emerges one of the first attempts to picture the Milky Way, not as a vague luminous band, but as a structured star system with extent and form. The image Herschel eventually produces is remarkable not because it is fully correct, but because it reveals the scale of the new ambition. Humanity is no longer content merely to locate planets or predict celestial motions. It is trying to map the entire stellar environment from within. This is a strange undertaking, almost like trying to chart the shape of a forest, while standing somewhere deep among the trees and seeing only a few trunks clearly at a time. Herschel concludes that the Milky Way is a great flattened system of stars, and that the Sun lies not far from its centre. Later work will revise this placement, showing that dust obscures vast regions and that the Sun is not central in the way Herschel imagines. But the deeper achievement remains. The stars overhead are no longer treated as a random scattering. They begin to cohere into a cosmic structure. Space acquires anatomy. That would already be enough to change the story of the universe. But the sky has prepared another complication. Scattered among the stars are hazy objects, faint luminous patches that resist easy classification. Some are diffuse and irregular. Some are compact and nearly featureless. Some reveal shapes that seem eerily organized, spirals, ellipses, glowing clouds with central condensations. These are the nebulae, and they carry a special power because they do not behave like ordinary stars. A star remains a point of light even in imperfect instruments. A nebula looks like a stain, a blur, a fragment of unresolved structure. It invites interpretation and resists certainty. To an observer already living inside the expanding idea of the cosmos, nebulae are profoundly destabilizing. They may be nearby clouds of luminous gas within the Milky Way. They may be clusters of faint stars too distant to resolve individually. Or they may be something far stranger. Entire stellar systems lying at such immense distances that even the best telescopes can only glimpse their collective glow. This last possibility is radical, because it would mean the Milky Way is not the whole universe or even close to it. It would mean that Herschel's growing map of the stars describes only one island in a much larger cosmic sea. The image of islands is important because it transforms the emotional scale of astronomy. A single great star system is already immense enough to destabilize old intuitions. A universe made of many such systems, scattered through dark space beyond one another, is almost impossible to picture. Yet some nebulae encourage exactly this thought. Their apparent forms seem too coherent to be random mist. Some resemble structures with centers and arms, as though they are self-contained worlds on scales that dwarf the Milky Way itself. The eye cannot prove this, but it begins to suspect it, and once suspicion enters the field, every haze in the night acquires a second life. A blur may no longer be a blur, it may be distance itself made visible. Herschel's own views shift over time. In some cases he resolves nebulae into swarms of stars, strengthening the belief that telescopes can peel away apparent fog and reveal hidden multiplicity. In other cases the haze persists. This persistence matters. A nebula that refuses to dissolve under stronger magnification behaves like a kind of message from beyond the reach of present instruments. It suggests either a fundamentally different kind of object, or a familiar kind placed at an almost unthinkable remove. The darkness of space thus becomes layered. There is the darkness between stars, the darkness between structures within the Milky Way, and perhaps a deeper darkness between whole stellar realms. The void is no longer a single interval. It becomes a hierarchy of separations, but the great obstacle remains distance. Herschel can count stars. He can infer broad shape. He can discover planets and catalogue nebulae. What he cannot yet do is measure the true remoteness of most of what he sees. Without reliable distance, structure floats loose from certainty. A bright star may be genuinely luminous or merely close. A faint star may be dim or unimaginably far away. A nebula may be a local cloud or a remote galaxy. The telescope gathers light, but light without distance can mislead as easily as it can reveal. The universe begins to seem full of forms that cannot be securely placed. This uncertainty gives the era its peculiar mixture of triumph and suspension. The sky is yielding more detail than ever before. Catalogues grow. Patterns emerge. The Milky Way begins to resemble a real system rather than a poetic band. Yet every new object seems to generate at least one new ambiguity. The stronger the instrument, the more space resembles an unfinished argument. Herschel does not merely discover things. He discovers how much there is that cannot yet be decided. The vast disk of stars he sketches may have an edge, but the appearance of edge may itself be an illusion created by limited reach. The nebulae may belong to the Milky Way, or they may stand beyond it in a darkness not yet measured. The map expands, but so does the unknown. This is how the mystery deepens. The universe is no longer a fixed shell, and it is no longer merely an abstract infinity. It is beginning to show texture, structure, density, and perhaps layers of organization far beyond anything earlier ages can imagine. Yet each gain in clarity also sharpens the sense that visibility itself is partial and conditional. The telescope does not simply reveal what exists. It reveals where vision fails. It shows star fields thickening into whiteness, then fading into black. It shows milky haze resolving into countless suns, and other haze remaining stubbornly unresolved. It shows enough to tempt a picture of everything and not enough to complete it. Space starts to look less like emptiness and more like a deep medium crowded with hidden arrangements. Some near, some far, some perhaps so distant that they masquerade as mist. In this way, the work of William and Caroline Herschel marks a turning point in the history of cosmic thought. They do not yet solve the problem of the universe. They do something more consequential. They force the problem into visible form. They show that the Milky Way can be treated as an object with structure. They show that the heavens contain categories of things not easily reduced to stars and planets. They bring into focus the possibility that the visible sky is only the local texture of a much larger reality, and they leave behind a universe that feels more alive, more organized, and more haunted by hidden depth than ever before. What had once been a dark dome over Earth now resembles an ocean filled with currents, shoals, and distant lights glimpsed through fog. The next step will require more than better mirrors. It will require a way to measure the abyss itself. The universe now has forms but not yet firm dimensions. The Milky Way appears as a great system. The nebulae hover at the edge of interpretation. The darkness between objects is beginning to look less empty than before, not because anyone has found substance there, but because distance itself has become a force in the story. A star is no longer simply a light. It is a question of remoteness. A nebula is no longer simply a haze. It is a question of scale. The same faint glow can mean small and nearby or vast and unimaginably far away. Without distance, the sky remains a theatre of appearances. The next transformation in astronomy comes from a decision that seems almost impossible at first to measure the depth of space directly, not by guesswork or analogy, but by geometry. The first usable method depends on one of the quietest motions in the heavens, the annual path of Earth around the Sun. Human beings do not feel this motion in ordinary life. The ground seems still, the sky seems to move, and the illusion of local stability survives because the scale is so large. But Earth traces a wide orbit through space, and that motion provides astronomers with two slightly different vantage points from which to view the nearby stars. The principle is familiar in ordinary life. A finger held at arm's length seems to shift against the background, when seen first with one eye and then the other. Near things move more than distant ones. The same logic, extended across the diameter of Earth's orbit, becomes stellar parallax. The brilliance of the method lies in its austerity. Nothing about the star itself needs to be known in advance. No assumption about true brightness is required. The star is watched at one time of year and then again 6 months later, when Earth is on the opposite side of its orbit. If the star is near enough, it will appear to shift slightly against the more distant background. From that tiny displacement, geometry yields its distance. The difficulty is that the shift is almost absurdly small. Even the nearest stars are so far away that their changes of apparent position are nearly swallowed by the limits of 19th century instruments. For generations, astronomers chase this effect and fail to demonstrate it convincingly. The failure itself is meaningful. It shows that the stars are not merely distant in a poetic sense. They are distant beyond intuition. When Friedrich Bessel finally succeeds in measuring the parallax of the star known as 61 Cygni in the 1830s, the result is more than a technical triumph. It is the first robust bridge from Earth into interstellar space. A star is no longer only a point of light whose depth can be imagined. It has become a measured location. The distance is staggering, on the order of many trillions of kilometers. Numbers at this scale do something peculiar to the mind. They do not merely enlarge. They weaken ordinary comparison. Even the orbit of Earth, which once seems enormous, becomes a tiny baseline used to probe an abyss. The solar system begins to look local in a new and humbling way, not because it has shrunk physically, but because the first step beyond it reveals how much farther the stars really are. Yet stellar parallax, for all its precision, carries a harsh limitation. It works only for the relatively nearby stars. The farther objects lie, the smaller their apparent shift becomes, until it vanishes into instrumental uncertainty. This means that the method can open the first gate into the Milky Way, but not the deeper gates beyond. The faint clusters and nebulae that trouble the imagination remain largely untouched. Their distances are still hidden. The cosmic map gains a few anchors, but not enough to settle the larger argument. A nearby star can now be placed with confidence, but a far nebula can still masquerade as almost anything. This is often how science advances at the larger scales. A method solves one realm and exposes the insufficiency of that solution for the next. Each answer behaves like a lamp lighting only the immediate ground, while beyond the circle of illumination the darkness gathers again. The parallax measurements make the stars real in a new sense. They also reveal the inadequacy of human position. Earth's whole orbit, vast enough to order the seasons and define the year, is still too small a tool for most of the galaxy. The observer begins to feel physically trapped inside a local pocket of knowable space, able to triangulate only the nearest neighbours while the greater architecture remains withheld. It is in this atmosphere of partial success that a second distance scale slowly emerges, not from geometry this time, but from pattern. At the Harvard College Observatory, where women often carry out painstaking analytical work without the recognition granted to male astronomers, Henrietta Swan Leavitt studies photographic plates of the sky with unusual patience and insight. Her work is not glamorous. It involves comparison, notation, and the disciplined inspection of tiny changes on glass images. Yet this apparent modesty conceals one of the most consequential discoveries in the history of cosmology. Leavitt studies variable stars, specifically a class now known as Cepheid variables, stars whose brightness rises and falls in a regular rhythm. These stars are not flickering randomly, they pulse. The crucial insight is not simply that they vary, but that their period of variation is tied to their intrinsic brightness. A Cepheid that pulses more slowly is, in general, truly brighter than one that pulses more quickly. This relation is profound because it transforms a changing star into a measuring instrument. If the pulse period reveals how bright the star really is, and its apparent brightness is also known from observation, then the distance can be inferred. What the star seems to be can be compared with what the star actually is. The discrepancy becomes a measure of remoteness. The elegance of this method is almost unsettling. Space yields another secret not by being crossed, but by allowing a pattern to be recognized. A star carries within its own behavior the clue to how far away it must lie. Leavitt does not herself use this relation to redraw the universe with a large telescope, but she supplies the key that others will use. The discovery is one of those moments when a patient act of classification alters the scale of reality. Before the period luminosity relation, the deeper universe remains largely out of reach. After it, the possibility appears of measuring far more distant stars, including those in other stellar systems, if such systems exist. The importance of this shift is hard to overstate. Parallax depends on the small motion of the observer. Leavitt's method depends on the internal regularity of the stars themselves. Together they begin to form what astronomers later call a distance ladder, a chain in which one method calibrates the next, allowing measurement to reach progressively farther outward. The nearest stars teach the true scale of Cepheids nearby. Those Cepheids then reveal the distances of more remote Cepheids, and from there, other structures may begin to yield, It is as though astronomy is building a bridge over emptiness plank by plank, each measurement supported by the last, each success carrying the risk that the next span may still collapse into uncertainty. The emotional atmosphere of this period is one of approaching revelation without quite attaining it. The Milky Way is known to be large, but how large remains uncertain. Nebulae are known to exist, but what they are remains disputed. Some astronomers continue to believe that the galaxy contains everything important. Others suspect the nebulae are external systems, island universes scattered through far greater depths. Evidence accumulates, but not yet in a form strong enough to compel general agreement. The sky is suspended between two radically different meanings. Either humanity lives inside the one great stellar system, and the strange hazes are local phenomena, or the Milky Way itself is only one structure among many, and the true universe is larger by orders of magnitude than even Herschel imagines. What makes this suspense so powerful is that it is not driven by fantasy. It is driven by method. The stars are beginning to give up measurable clues. The void is not yielding to poetic speculation alone. It is being interrogated by repeated procedures, by photography, by careful plate comparison, by timing cycles of light, by reasoning from brightness and motion. Yet the deeper the measurement reaches, the more the darkness seems to reorganize itself. Every gain in distance does not simply fill space with known objects, it enlarges the arena of uncertainty. A nebula that once sits vaguely among the stars may, under the new logic, become a possible galaxy. A dim point that once seems negligible may become a marker of inconceivable depth. There is also a subtler mystery beginning to take shape. Distance is not merely a number attached to an object. It changes the nature of what observation means. To see far is to see late. The further a star or nebula lies, the older the light that arrives from it. Thus the act of measurement begins to carry time inside it. The universe is not only spatially deep, it is historically layered. Even before the full consequences of this fact are understood, the foundations are being laid. The light from a remote star has already travelled through years, decades, perhaps vastly longer intervals. The blackness between Earth and that star is not passive emptiness. It is the route through which the past arrives. That growing fusion of distance and delayed light makes the unresolved status of the nebulae more disturbing than before. If they are nearby clouds, one set of questions follows. If they are remote star systems, an entirely different reality opens. In that case, the faint smudges on photographic plates are not local curiosities. They are ancient messages from regions so far away that their light began travelling long before modern observers were born. The sky would then be filled not only with stars but with histories separated by enormous reaches of both space and time. The darkness between them would no longer look like blank separation. It would look like accumulated delay, the vast medium through which the visible universe is staggered into awareness. Henrietta Leavitt's discovery quietly prepares the way for this conceptual rupture. She does not simply make a measuring tool. She destabilizes the scale of the cosmos by making deeper measurement possible. The great question of the nebulae, which has long hovered in ambiguity, now moves toward a possible answer. The Milky Way is about to be tested against a larger claim. Either it is the universe entire, or it is not even close. The choice will not be settled by intuition, because intuition has already failed too many times. It will be settled by distance, by whether certain variable stars embedded in the hazes prove them to be local or impossibly remote. At this threshold, the universe feels poised between containment and dispersal. Everything learned so far has enlarged it, but enlargement has limits. A galaxy can still be imagined as the whole. The stars can still be gathered into one immense but singular system. the darkness can still be treated as the interval inside a larger unity. But the new methods are preparing a harder verdict. The abyss is becoming measurable, and once that happens, the old comfort of a single cosmic homeland may not survive. The next step will not merely revise the map, it will break the scale of existence open again, and the black between the stars will widen into something far more severe than distance alone. By the early 20th century, the argument over the nebulae grows into one of the most important disputes in astronomy, because it is no longer only about a few faint objects. It is about the size of reality itself. If the Milky Way contains everything visible in the heavens, then the universe is vast but singular, one great stellar system embedded in darkness. If the spiral nebulae are separate systems lying far beyond it, then the visible cosmos is fragmented into immense islands of stars scattered across even deeper space. In one picture, humanity stands somewhere inside the total structure. In the other, it stands inside only one province of a far grander arrangement. The same hazy forms in the telescope support both possibilities, which gives the debate its peculiar tension. The evidence is close enough to provoke conviction and incomplete enough to sustain contradiction. Some astronomers gather reasons to believe the Milky Way is nearly all there is. Its star fields are immense. Its cloudy band circles the sky with such dominance that it seems natural to treat it as the primary body of the universe. Globular clusters, gathered in swarms, appear to define a large stellar domain around it. The spiral nebulae, under this view, are local objects, perhaps forming star systems or clouds within the wider galactic environment. Others study the same sky and feel the scale is still too small. Some nebulae display such organized structure, such coherence of form, that they seem less like local scraps and more like self-contained worlds. Their spirals look deliberate. Their central bulges suggest concentration. Their faint outer arms resemble enormous systems seen from impossible distances. The eye has no final authority here. It can only report shapes suspended in uncertainty. This is the setting in which Edwin Hubble arrives at Mount Wilson Observatory. He enters astronomy at a time when the field is becoming inseparable from large machines. The old age of hand-built mirrors and private observatories has not vanished, but the frontier now belongs increasingly to great instruments raised on remote mountains under dark skies. The Hooker telescope, with its immense mirror, is the most powerful optical telescope of its era. It does not simply magnify. It gathers light from depths that earlier observers can barely suspect. That distinction matters because remote structures do not first announce themselves through size. They announce themselves through faintness. The problem with the spiral nebulae is not merely that they are small in the field of view. It is that they lie, if the bolder interpretation is correct, at distances so great that even large systems arrive as whispers of light. Hubble is well suited to this moment, not because he is alone in talent, but because astronomy has reached a point where temperament, opportunity, and method suddenly align. The question of the nebulae has ripened. Leavitt's work on Cepheid variables has supplied the means to measure great distances if such stars can be identified within the hazes. Photography has become good enough to preserve faint details for repeated examination. Telescopes have become powerful enough to search within structures that once look almost featureless. The universe has prepared a narrow opening, and Hubble steps into it. The Andromeda Nebula becomes the critical object. It is bright enough to command attention, large enough to reveal hints of structure, mysterious enough to matter. Even to modest instruments, it appears as a diffuse, elongated glow. Under stronger scrutiny, it shows a more complex form, a great central concentration surrounded by dimmer extensions, with dark lanes threading through luminous regions. It does not look random. It looks organized, almost architectural, yet organization alone proves nothing. A nearby cloud can be organized. A distant galaxy can be organized. The question is still one of scale. How far away is Andromeda really? Hubble studies photographic plates of Andromeda with extraordinary care, searching for stars that vary in brightness over time. This is delicate work because the field is crowded and the target faint, but eventually the search succeeds. Cepheid variables are identified within the nebula. This is the turning point. Once a true Cepheid is found, its pulsation period can be measured. Once the period is known, its intrinsic brightness can be inferred from the relation established by Henrietta Leavitt. Once intrinsic brightness is known, the distance follows. The logic is almost merciless in its simplicity. Either the object lies within the Milky Way or it does not. The star's pulse will decide. When the result arrives, it is devastating to the smaller universe. Andromeda is far beyond the accepted dimensions of the Milky Way as then understood. It is not a local cloud. It is not a minor appendage inside the home galaxy. It lies at a distance so large that only one interpretation remains plausible. It is itself a vast stellar system. What appears in the sky as a soft patch of light is in fact an immense congregation of stars. The hazy blur resolves conceptually before it fully resolves visually. Distance transforms appearance. The nebula ceases to be a nebula in the old sense. It becomes another galaxy. This is one of the rare moments in science when a single class of measurement changes the emotional architecture of existence almost overnight. Before the result, the Milky Way can still be imagined as the universe entire. After the result, that belief becomes untenable. The spiral nebulae can no longer be comfortably treated as local curiosities. If Andromeda is a separate galaxy, then many other spirals likely are as well. The sky is not filled merely with stars inside one grand system. It is filled with systems of stars. The faint background smudges that earlier astronomers catalogue with uncertainty now begin to take on an almost unbearable significance. Each may contain billions of suns. Each may be a world of structure, motion, birth, and death on scales comparable to or exceeding the Milky Way. At once, the darkness between galaxies acquires a new severity. The distances inside the Milky Way are already enormous, but they now become local distances. Between one galaxy and another lies a deeper black, a gulf so wide that light itself takes millions of years to cross it. Andromeda is not simply far. It is far enough that the light entering an observatory mirror has been travelling since before recorded history in its modern forms. When a human eye eventually receives those photons, it receives a past. This is not metaphor. It is the literal structure of observation. To look out is to look back. Every gain in distance is also a gain in antiquity. That fact begins to alter the meaning of the universe more fundamentally than the discovery of additional galaxies alone. If the sky is populated by many stellar systems, each seen at a different stage of its history, then the visible cosmos is not a snapshot. It is a time-layered tapestry. Nearby stars appear almost current by astronomical standards. Distant galaxies appear ancient. More distant galaxies still, once later instruments find them, will appear as they existed when the universe itself was younger. The darkness between objects is therefore not empty spacing in a static arrangement. It is a depth charged with delay. The void becomes the medium through which time is sorted and delivered, and yet the revelation does not produce clarity in all directions. It resolves one mystery by generating another. If galaxies are scattered through immense space, how many are there? How far does this distribution continue? Is there an edge to the galactic population? Does the universe as a whole have a shape or a boundary? The Milky Way is demoted from totality to membership, but what kind of membership remains uncertain? A galaxy may be one of many without the greater pattern being understood. The universe has become larger in a dramatic sense, but not necessarily more comprehensible. In some ways it has become less so, because the nearest successful answer has only exposed the next scale of ignorance. Hubble's work also sharpens the old question of darkness. Thomas Digges imagines infinite stars in infinite space, and encounters the paradox of the dark night sky. The discovery of external galaxies does not remove that paradox, it intensifies it. There are now vastly more stars than many earlier astronomers suppose, arranged not only across one galaxy, but across an immense population of galaxies. The universe is filling with light-bearing structures at every and large scale. Why, then, does darkness continue to dominate? The answer will soon involve motion, history, and the finite travel time of light. But at this stage, the contradiction grows more acute. The greater the abundance of luminous systems, the more meaningful the surviving blackness becomes. There is also a subtler and more unsettling implication in the Andromeda result. Once the spiral nebulae are understood as galaxies, the familiar human relation to the sky changes in a way that is difficult to reverse. The stars visible to the naked eye belong mostly to one local system. Beyond them lies an entire additional population of realities too faint to dominate direct vision. Ordinary sight is revealed as provincial. The sky that looks complete to unaided perception is not complete at all. It is a foreground. Behind it stand countless larger structures hidden by distance and limited brightness. That means reality has been layered all along, with a deeper order present but inaccessible until technology and inference reach the necessary threshold. The visible universe is not false, it is incomplete in a systematic way. This incompleteness invites the next stage of speculation. If one level of apparent reality conceals another, might the newly visible level also conceal more? Galaxies become the basic units of large-scale structure, but perhaps they themselves are arranged into greater patterns, clusters, superclusters, filaments, voids. These concepts will later emerge as astronomy surveys the cosmos more broadly. Even here, the logic is already latent. Once the universe ceases to be a single stellar system, there is no reason to assume the next revealed scale is final. Every new depth may itself be part of a deeper arrangement, visible only when instruments, methods, and patience improve again. Andromeda therefore stands as more than a neighbouring galaxy. It is a threshold object, the place where a blur becomes a system and where astronomy crosses from galactic thinking into cosmological thinking. The old home remains immense, but it no longer feels singular. The mind begins to picture the Milky Way suspended among other great islands of stars, all separated by black reaches so wide that ordinary language strains to hold them. The darkness between stars has become the darkness between galaxies, and that shift changes the nature of emptiness itself. Empty space is no longer simply the room left over after matter gathers. It is the principal dimension of the cosmos, the dominant setting within which all luminous systems are scattered like rare settlements in an almost measureless night. Yet even this is not the end of the disturbance. If Andromeda and the other spiral nebulae are galaxies, then their light must cross the intergalactic void to reach Earth. That means the void is not opaque, it transmits. But it also does not transmit everything in any simple sense, because the darkness survives. Some light arrives, some does not, and the reasons are not yet fully known. The black between galaxies begins to look less like mere emptiness and more like a condition with consequences. It preserves separation. It imposes delay. It allows ancient light to travel, yet withholds the total blaze that an eternal static universe would produce. It is not merely what lies between structures. It is part of the logic by which those structures are seen at all. This is how the discovery of island universes widens the mystery even as it settles the debate. The cosmos is no longer one great city of stars but an archipelago extending into remote darkness. The observer stands inside one galaxy while receiving delayed signals from others, each a vast world of suns. The night sky becomes deeper, older, and more layered than any earlier generation can easily imagine. And the old question returns with renewed force. If so much exists beyond the Milky Way, why does the universe still look so dark? The answer will not come from counting more stars. It will come from understanding space itself, because the next revelation is stranger still. The black between galaxies is not still. It has a geometry, a history, and perhaps a power of its own. The discovery of galaxies settles one argument only to expose a deeper one. The universe is now known to be larger than the Milky Way, perhaps vastly larger, and the darkness between its great structures is no longer a merely visual absence. It has become the dominant fact of cosmic architecture. Stars gather into galaxies separate across enormous reaches, and the overwhelming majority of the visible universe consists not of matter, but of the intervals between concentrations of matter. At first, this seems to simplify the problem. Space is just what lies between things. It is a gap, a stage, a neutral emptiness. Matter shines, moves, and collides within it, while space itself remains silent and featureless. This view is appealing because it matches ordinary intuition. A room appears to be defined by its contents and boundaries. Remove the furniture, and what remains seems passive. Remove every object entirely, and it becomes difficult to imagine that anything meaningful is left. Yet astronomy is pushing toward a point where that common sense begins to fail. The more precisely the universe is measured, the less convincing it becomes to treat space as nothing more than blank extension. The first challenge to this intuition comes not from an observatory, but from geometry. For centuries, the geometry of Euclid supplies the invisible rules by which physical space is understood. Straight lines remain straight. Parallel lines never meet. The angles of a triangle add to a fixed total. These are not treated merely as abstract truths inside thought. They are treated as the natural grammar of the world itself. A wall, a road, a roof beam, the edge of a field. All seem to confirm that ordinary space is flat and reliable. The mind begins with nearby experience and extends it outward. If a room behaves this way, why should the cosmos not behave this way as well? The assumption is so deeply embedded that it becomes difficult even to imagine an alternative. Yet a subtle difficulty lies hidden inside that confidence. Euclidean geometry describes flat surfaces and flat space. But nature is not obliged to remain flat merely because local experience encourages the belief. The surface of Earth already provides a clue. To someone moving across a small region, the ground appears level enough, and the ordinary rules of geometry work well. But on larger scales, those rules begin to bend. Meridians on a globe can be thought of as lines that start out parallel near the equator and meet at the pole. Triangles drawn across the surface of a sphere can contain more angular sum than flat intuition permits. The world behaves as though geometry depends on the shape of the arena itself. Carl Friedrich Gauss is among the first to push this insight toward a more radical possibility. He studies curvature not as an illusion imposed by embedding a surface in some larger space, but as something that can be detected from within the surface itself. This is a subtle but momentous shift. It means that an inhabitant confined to a curved realm need not step outside it to know that curvature exists. Measurements made internally, by comparing paths and angles, can reveal the truth. A surface does not need an external witness to possess geometry. Geometry is intrinsic. This idea, quiet at first glance, destabilizes one of the oldest habits of thought. Space no longer needs to be judged from outside. It may carry its own signature within itself. Gauss does not yet fully break common sense, but he prepares the tool that will break it. If a two-dimensional surface can have curvature detectable from within, then perhaps higher dimensional spaces can also possess curvature without requiring some visible external bending. This is where Bernhard Riemann enters the story with astonishing boldness. In the middle of the 19th century, he extends the notion of geometry far beyond flatness and even beyond surfaces. He imagines spaces of any number of dimensions, each with their own internal rules of distance, direction, and curvature. To mathematicians, this is an act of liberation. To ordinary physical intuition, it is almost intolerable. A curved surface can at least be pictured by bending paper or tracing a sphere. Curved three-dimensional space cannot be easily pictured at all, because there is no simple external vantage from which to view it. One lives inside it, one measures it from within, one can detect its effects without ever seeing it as a whole. This is the point at which emptiness begins to lose its innocence. If space can be curved, then empty extension is not just a container. It has structure. It may possess local properties. It may determine how straight motion behaves. Even before physics fully absorbs the idea, the conceptual transformation is severe. What had seemed like a passive gap between objects becomes something that can differ from place to place. A straight path may not be globally straight. Distance itself may depend on the geometry of the region through which it is measured. The darkness between stars and galaxies begins to look less like blank separation and more like a medium with hidden form. For decades, this remains largely a mathematical provocation. The astronomy of galaxies, stars, and nebulae continues to advance through instruments and observation. The strange geometries of Gauss and Riemann hover nearby, elegant but detached from the visible sky. Then Albert Einstein draws them into physical reality. His general theory of relativity does not simply revise gravity, it rewrites the relationship between matter and space. In the older Newtonian picture, gravity acts as a force pulling masses toward one another across otherwise passive space. The stage remains unchanged while the actors attract. In Einstein's picture, the stage is no longer fixed. Mass and energy influence the geometry of spacetime itself, and objects move along the curves that result. What appears as gravitational attraction is, in deeper description, motion through a warped structure. This is one of the great reversals in the intellectual history of the universe. Gravity, once imagined as an invisible pull operating through emptiness, becomes evidence that emptiness is not empty in the old sense at all. Space responds, it bends, time is drawn into the same fabric, so that duration and distance cease to be separate backgrounds and become interwoven aspects of a single changing reality. Matter tells space-time how to curve, and curved space-time tells matter how to move. The concise beauty of that idea hides its strangeness. The planets no longer orbit merely because the sun pulls them across a neutral void. They follow the structure of a region whose geometry is shaped by the sun's presence. Light itself does the same. Even a beam of light passing near a massive body is deflected, not because it has weight in the old sense, but because the geometry through which it travels is altered. The confirmation of this idea arrives dramatically when starlight is observed bending near the sun during an eclipse. The effect is small but real. Light coming from stars behind the sun appears shifted because its path is curved by solar gravity. This is more than a vindication of a theory. It is a revelation about the nature of the dark between objects. The space around the sun is not a blank interval through which light passes unchanged. It is a geometrical field. It shapes routes. It changes what is seen. The old concept of empty space as featureless nothingness becomes much harder to sustain. The consequences spread quickly. If space-time responds to mass and energy locally, then on the scale of the entire universe it cannot simply be assumed to remain static and flat. Once Einstein writes down the equations of general relativity, those equations begin to suggest something unexpected and deeply troubling. A universe filled with matter does not sit quietly in perfect balance by default. The large-scale geometry evolves. It can expand or contract. The cosmos, taken as a whole, need not be a stable container. It can be dynamic. Einstein himself hesitates before this implication. The thought that the entire universe might change in size seems too radical, even to a mind already willing to abandon old concepts of space and time. To preserve a static cosmos, he adds an extra term, the cosmological constant, to counteract gravitational collapse. That hesitation reveals how deeply the old preference for cosmic stillness persists. Even after space becomes curved and active, it remains psychologically tempting to imagine the universe as a grand but unchanging whole. Yet the mathematics resist that preference. The geometry of space-time on cosmic scales seems to demand history. It does not want to stay still. Here the mystery of emptiness takes another step forward. Space is not only structured, it is capable of changing as part of the evolution of the universe. The black between galaxies may grow, shrink, stretch, or distort. Emptiness begins to resemble a participant in cosmic events rather than a passive backdrop. There is a peculiar emotional effect in this transition. The night sky had once suggested a fixed ceiling. Diggers breaks the ceiling and introduces endless depth. Herschel and Hubble populate that depth with galaxies. Einstein now changes the depth itself. The darkness between luminous things is no longer simple room. It has geometry, behavior, and perhaps even destiny. To think this way is to let go of one of the last old comforts. There is no final stable stage behind the motions of the universe. The stage is in motion too. Speculation naturally gathers around this new picture because once space has properties, further questions become unavoidable. If curvature can exist where little matter is present, how empty is empty space ever allowed to be? If light follows the geometry of the void, can the void trap or redirect information in ways not obvious at first glance? If space-time can bend, perhaps under extreme conditions it can ripple, twist, or fold in manners that later generations will only begin to test, even before gravitational waves are directly observed. The theory already hints that space-time is capable of carrying disturbances across the cosmos. Empty space may ring with consequences long after violent events occur. The void becomes something that can remember motion in the form of travelling curvature. At the scale of daily life, none of this is visible. Rooms still look Euclidean. Floors appear level. Empty space still seems empty. That contrast between local simplicity and cosmic strangeness adds to the unease. Reality behaves in two registers at once. Nearby experience persuades the mind that emptiness is nothing of consequence. The universe at large steadily teaches the opposite. Stars move through bent geometry. Galaxies occupy a dynamical space-time. Light is delayed, redirected, and limited by the structure of the void itself. The black regions on astronomical photographs are no longer merely the parts where nothing shows up. They are signs of the underlying medium within which everything occurs. This shift also reframes the old paradox of darkness. A static infinite star field already produces contradiction. But now static infinity is not even the natural default. The geometry of the cosmos has its own evolution. Space itself may be changing, and that change may help explain why darkness survives despite the abundance of light. The answer is not here yet in full, but its outline is taking shape. Once space becomes dynamic, The night sky cannot be understood by counting stars alone. The properties of the void must be included. Distance is no longer fixed. Geometry is no longer absolute. And the black between galaxies may be stretching under conditions no human eye can directly feel. In this way, the work of Gauss, Riemann, and Einstein completes a conceptual reversal that began when the fixed shell of stars first cracked. The heavens are not enclosed. The stars are not all part of one local system. The galaxies are not suspended in a passive emptiness. Every step away from the old picture gives more authority to the void. What seemed least substantial becomes increasingly central. Space acquires form, flexibility, and influence. It ceases to be the mere absence of matter and becomes a component of physical reality, one that can shape motion, alter light, and perhaps govern the fate of the whole cosmos. The next stage of the story will reveal just how radical that claim becomes, because once astronomers look carefully enough at the light from distant galaxies, they begin to find that the emptiness between them is not only curved, it is expanding. Once space is allowed to possess geometry, the next question arrives almost uninvited. What is the geometry of the universe as a whole doing over time? It is one thing to say that mass curves space-time around stars, planets, and galaxies. It is another to say that the entire cosmic arena may itself be changing. Yet Einstein's equations point in exactly that direction. They do not sit comfortably with a universe frozen in eternal balance. Under most natural conditions, a cosmos filled with matter tends to evolve. It contracts or expands. It does not remain perfectly still. This implication is so strange that even Einstein recoils from it. The thought that space itself might be in motion, not as an object moving through some larger background, but as the very framework of distances changing from within, seems to violate the last ordinary intuition still standing. The stars can move, galaxies can drift, but how can space, the thing through which motion is measured, expand? For a time, the idea remains mathematical, suspended between possibility and disbelief. Then observation begins to close the gap. The light from galaxies does not arrive unchanged. When broken into spectra, those fine patterns of colour that reveal the fingerprints of chemical elements, the lines appear displaced. In many distant galaxies they are shifted toward the red end of the spectrum. This redshift can be understood through an effect already familiar in principle. A source of waves moving away from an observer stretches the waves it emits. With light, that stretching means a shift toward longer wavelengths, toward red. A receding object therefore announces its retreat through the altered character of the light it sends. Vesto Slipher begins measuring such shifts in the early 20th century and finds something remarkable. Many spiral nebulae are not merely moving, they are moving away at great speed. Their spectra carry the marks of recession. This result is unsettling even before the full cosmological meaning becomes clear, because it suggests that the universe is not a quiet arrangement of galaxies resting in place. Motion is everywhere, and at scales beyond anything that belongs to ordinary stellar systems. Yet the deeper pattern is not immediately obvious. It takes the later work associated with Edwin Hubble, building on distance measurements and redshifts together, to show that the recessional behaviour of galaxies is not random. It follows a law-like trend. The farther away a galaxy lies, the faster it appears to be receding. That pattern is one of the great clues in science, because it points toward an interpretation stranger than the raw data alone. If every distant galaxy is moving away, one tempting image is that the Milky Way occupies some special central point from which everything is fleeing. But the mathematics of expanding space offers a different and far more unsettling picture. The galaxies are not necessarily rushing through a pre-existing emptiness away from one privileged location. Instead, the space between galaxies is stretching. Distances grow because the underlying metric of the universe changes. Every galaxy sees others withdrawing according to the same basic rule, not because one galaxy stands at the true center, but because the fabric of separation itself is increasing. This idea is difficult because it asks the mind to stop picturing the universe as a collection of objects moving inside a larger static room. There is no outside room in the usual sense. There is no simple external vantage from which the universe expands into a surrounding void. Expansion means that the internal distances between unbound structures change with cosmic time. It is more like a pattern drawn on a surface that stretches everywhere at once, except the surface here is not a visible sheet, and the stretching happens in three-dimensional space, joined to time, without requiring a surrounding container. Galaxies remain mostly intact locally because gravity binds them. The vast separations between clusters and superclusters, however, widen. The black between the great lights deepens. This changes the meaning of emptiness again. The void is no longer just the interval that matter leaves unused. It is the very thing whose behavior determines the large-scale evolution of the universe. Empty regions are not fixed. They can grow. The space between galaxies has a history. Distances measured in one cosmic era are not the same distances in another. A beam of light launched across the abyss does not simply cross a motionless gap. The gap itself changes while the light travels. This is why ancient photons coming from deep space reach Earth carrying more than an image. They carry the signature of altered space. Their wavelengths are stretched along the way. The universe writes its own expansion into the light that survives crossing it. Once this becomes clear, the old paradox of darkness begins to reorganize itself around time and history. A universe that expands cannot be treated as a static eternal starfield. Its geometry evolves. Its contents were closer together in the past. Rewind the observed expansion backward and the galaxies approach one another. Go far enough, and the known universe once occupies a denser, hotter, smaller state. The exact nature of the beginning remains a matter for theory and caution, but the broad implication is difficult to avoid. The cosmos has not existed forever in its present form. It has a past in which conditions differ radically from those of the current era. Darkness is therefore no longer merely a puzzle about how light is distributed. It is bound to the finite age of luminous structures and to the limited time light has had to travel. This is the moment when cosmology begins to acquire something like narrative. The universe is not simply there. It develops. Galaxies form. Distances grow. Light is emitted in one state of the cosmos and received in another. The black between systems becomes historical space, not just geometric space. To look outward is increasingly to read traces of an unfolding sequence. Nearby galaxies appear in one chapter, far galaxies in earlier chapters, and the faintest remote structures later observed by advanced instruments in chapters earlier still. The universe becomes an archive whose pages are separated by darkness. There is a curious resistance in human thought to accepting this fully. Part of the resistance is intellectual. Expansion is not easy to picture. Part of it is emotional. A dynamic universe feels less secure than a static one. A cosmos with a history invites the suspicion of a beginning, and beginnings carry implications that science must approach carefully, without theological haste and without philosophical panic. Yet the evidence grows. Redshifts are not isolated oddities. They are systematic. Independent observers refine them. Distance indicators improve. Larger surveys strengthen the pattern. The recession of galaxies becomes one of the foundational observations of modern cosmology. And still the mystery does not simply shrink under explanation. It enlarges in a different way. If space expands, what governs the rate? Why does the geometry take this form rather than another? Was the early universe perfectly smooth or only almost smooth? How did the first galaxies emerge from the young cosmic state? These questions gather at once around the new picture, but another deeper one remains just beneath them. What exactly is stretching? The ordinary language of expansion risks suggesting a substance thinning out inside a larger emptiness. But that image is misleading. Space is not a gas or fluid in the simple sense. The distances defined by spacetime itself change. The void is not a material sheet visible to the eye, yet it behaves with enough regularity to imprint patterns on the largest observable scales. It acts like a physical ingredient without being an object in the ordinary inventory of things. This peculiar status gives empty space an almost ghostly authority. It has no colour, no smell, no texture accessible to human senses. It is not grasped directly. It is inferred through motion, light, delay, curvature, and scale. Yet its inferred behaviour becomes more powerful than many visible things. A galaxy shines brilliantly but only occupies a small region. Space, though dark, controls the relation between all such regions. Matter can cluster, radiation can travel. But the universe at large evolves according to the changing geometry of the emptiness that separates its luminous islands. The void becomes the hidden protagonist of cosmology. The finite speed of light now reveals its full significance. In a static eternal universe, light from infinitely many stars should eventually fill the sky. In an expanding universe with a finite age, not all light has had time to arrive. Some regions lie beyond the current horizon of observability. Their signals are still en route, or perhaps can never reach the observer at all if the intervening expansion grows too strong. Darkness therefore gains a new interpretation. It is not always the mark of literal nothingness. It is often the mark of inaccessible history. The black sky contains places from which light has not yet arrived, and perhaps places from which it never will. This introduces the idea of the observable universe, a concept as unsettling as any earlier cosmological revolution. What exists and what can be seen are no longer assumed to coincide. The visible cosmos is a limited sphere defined not by a physical wall, but by the age of the universe and the travel time of light through expanding space. Beyond that horizon, there may be more galaxies, more structure, perhaps vastly more reality continuous with what is already known. But direct knowledge is bounded. The universe reveals itself only within the region from which signals have been able to reach the observer since the cosmic beginning. Darkness at the edge of visibility is not merely absence. It is the frontier imposed by time and expansion together. There is an austere beauty in this answer, but it is not complete comfort. It explains why darkness survives, yet in doing so it makes the universe more strange. The night sky is dark not because the cosmos is poor in light, but because light is finite in speed. The universe is finite in age, and space itself changes while radiation travels. The explanation turns emptiness into process. The void is not what remains when stars are removed. It is what stretches between them, what delays them, what carries their ancient light while altering its wavelength, and what sets the horizon beyond which the current universe remains unseen, as the implications deepen. Another thought begins to stir, cautious but persistent. If space can expand now, what was it doing in the earliest moments? If the present universe shows redshift and large-scale growth, perhaps the young universe experienced phases of behaviour even more extreme. Perhaps expansion in the beginning was not gentle but violent. Perhaps the conditions from which the cosmos emerges were so dense and hot that familiar categories almost fail. Such speculation will later mature into more detailed models. But even here the essential mystery is visible. Empty space is not merely present after creation or after structure forms. It is implicated in the entire arc of cosmic history. From the earliest known states to the remote future, the void participates. The discovery of expansion therefore completes another reversal. The night sky first appears dark because daylight has ended. Then darkness becomes a paradox in an infinite star field. Then galaxies multiply and deepen the puzzle. Now the answer begins to emerge, not as a simple subtraction of stars, but as a consequence of cosmic history written into the geometry of space. The black between galaxies is stretching, carrying light and withholding light, creating horizons and remoteness, turning the universe into an evolving landscape of visible islands in a sea of growing distance. Yet the more fully this is understood, the less the void resembles nothing. It behaves too consistently, too powerfully, too centrally. It shapes the fate of light and the scale of the cosmos. And soon another relic will appear, one that does not come from stars or galaxies at all, but from an earlier time before either existed, filling the whole universe with a dim signal that reveals the first dawn hidden inside the dark. If the expanding universe points back toward a denser and hotter past, then a difficult possibility begins to harden into expectation. In the early cosmos, matter and radiation must once have been crowded together under conditions unlike anything familiar in the present sky. Galaxies do not yet exist. Stars do not yet burn in stable generations. Even atoms, in the ordinary sense, do not yet survive for long. The universe is instead a bright, hot medium in which light cannot travel freely across large distances because it is constantly scattered by charged particles. Space is already there, or at least the expanding fabric described by cosmology is already evolving, but it is not transparent. It is more like a fog of energy and matter so dense that the idea of seeing through it barely applies. This image, strange as it is, carries a consequence. If the universe later cools enough for atoms to form and for radiation to move freely, then some trace of that release of light should remain. The cosmos should still be filled with a weakened afterglow from its own early fire. This prediction is one of the most haunting in science, because it suggests that the darkness of the sky might contain not only the missing light of distant stars, but a relic from before stars existed at all. The black above Earth is not truly empty even to ordinary instruments. Hidden inside it is a bath of microwave radiation arriving from all directions, almost perfectly uniform, faint and cold by present standards, yet originating in an epoch when the whole observable universe is far hotter and brighter than any galaxy today. This is not starlight. It does not come from suns scattered through later cosmic history. It is older than galaxies. It is a residue of the moment when the young universe first becomes transparent. The accidental discovery of this radiation in the 1960s gives the expanding universe something more than elegant theory. It gives it a fossil. Arno Penzias and Robert Wilson, working with a radio antenna, encounter a persistent background signal that seems to come from everywhere. At first it behaves like interference without a source. It does not vanish with improved calibration. It does not track any ordinary local contamination in a simple way. It is just there, a low hiss spread across the sky. At nearly the same time, other physicists are thinking seriously about the predicted relic radiation of a hot early universe. The fit is extraordinary. The hiss is not noise in the dismissive sense. It is a remnant of primordial light, stretched by cosmic expansion from intense shorter wavelengths into the microwave regime. This changes the meaning of darkness with remarkable force. The sky remains visually black because the ancient radiation is no longer visible to human eyes. Expansion has diluted and cooled it over billions of years, lengthening its wavelength until it inhabits a different part of the spectrum. But the darkness is now known to be filled with a signal from the first great clearing of the cosmic fog. The void is not silent. It glows in microwaves. The universe carries a background memory of its own youth. What that youth looks like in broad outline is one of the strangest reconstructions ever achieved by human thought. In the beginning stages accessible to current cosmology, matter and radiation exist in a hot, dense state. As expansion proceeds, temperature falls. Eventually, protons and electrons combine to form neutral hydrogen. This process matters because free electrons are extremely effective at scattering light. When most of them become bound into atoms, radiation suddenly gains the ability to travel long distances without constant interruption. The cosmos becomes transparent. Light that has until then been trapped in a churning plasma can at last stream outward. That release is not a local event happening at one place. It occurs throughout the young universe. Every region becomes, in effect, a source of newly liberated light. The afterglow of that transition survives to the present because light keeps travelling, and because the universe keeps expanding. As space stretches, the wavelengths of the ancient photons stretch with it. What begins as intense radiation in the early hot cosmos gradually cools into microwaves. The entire observable universe becomes filled with this relic field, now measured with extraordinary precision by satellites and observatories. Missions such as COBE, WMAP, and Planck refine its properties and reveal that it is not perfectly smooth. Tiny variations in temperature, minute ripples in what otherwise appears almost uniform, mark the seeds from which later cosmic structure grows. Those ripples carry another layer of mystery. They are astonishingly small, yet without them the universe would look very different. If the early cosmos were perfectly even, matter would have little reason to gather into the stars, galaxies, and clusters seen today. The slight differences in density recorded in the relic radiation become the beginnings of later structure. Gravity slowly amplifies them. Over immense spans of time, faint irregularities grow into the cosmic web, the great filaments and nodes along which galaxies assemble. This means that the microwave background is not merely evidence that the universe once blazed, it is also a snapshot of the universe before its visible architecture fully forms. It is a portrait of potential. The darkness of the modern sky, when observed in the right wavelengths, conceals the pattern from which later luminous structures emerge. Here the notion of empty space becomes even more elusive. The young universe before recombination is not empty in any ordinary sense. It is crowded, energetic, opaque. But once transparency arrives and expansion continues, the relic radiation begins its long passage through a cosmos whose great structures are still only developing. The same space that later separates galaxies first acts as the medium in which primordial light streams outward almost uniformly. Then, as matter gathers, the geometry and content of the universe start to complicate that passage. The void is never simply blank. It evolves from a hot, dense field of interaction into a cooler, expanding arena carrying an ancient signal across billions of years. The microwave background also gives a refined answer to the old question of why the night sky is dark. Darkness does not mean there is no light. It means the dominant ancient light has been shifted beyond visible wavelengths, while the visible light from stars and galaxies is limited by cosmic age, distance, and expansion. In other words, the sky is black to human sight not because the universe lacks radiance, but because much of its most fundamental radiance arrives in forms the eye cannot register. The visible darkness is therefore a kind of sensory boundary. Human vision reports absence where instruments reveal a nearly all-encompassing glow. That realization carries a quiet philosophical tension, though the story need not state it as philosophy. The universe is filled with evidence that does not announce itself to unaided senses. Ordinary sight, even under a perfect night sky, shows only a thin slice of reality. Behind the visible stars lies the microwave afterglow. Behind that, the inferred hot early state. Behind that, perhaps even earlier processes not yet fully understood. Every widening of the electromagnetic window reveals that darkness is relative to the observer's apparatus. Blackness is not the same as nothingness. It is often what remains when the wrong instrument is used. The precise maps of the cosmic microwave background deepen this unease by suggesting that the observable universe is only a bounded chapter of a larger whole. The background appears as a sphere around the observer, not because Earth occupies a special cosmic center, but because every observer in an expanding universe can only see outward to the limit from which ancient light has had time to arrive. The last scattering surface, the effective origin of the background radiation, is a horizon defined by history. It marks the farthest epoch from which electromagnetic information can currently reach the present observer. Beyond it lies earlier plasma, and beyond that, in a practical observational sense, a deeper obscurity. The universe becomes knowable in shells of access, each one bounded by physical conditions rather than by walls. That is a subtle but profound shift in the meaning of frontier. Earlier ages imagined the edge of the universe as a shell or limit in space. Modern cosmology replaces that image with horizons determined by time, transparency, and expansion. There may be no sharp outer boundary to the total cosmos in the old pictorial sense, yet there is a real limit to what can presently be seen. The observable universe is finite in this practical way. It contains all regions whose light has had time to arrive since the beginning of cosmic transparency, or since the broader beginning of expansion, when interpreted more carefully through current models. Outside that observable region, if outside is even the right word, there may be more of the same, or perhaps patterns too large to notice from within one horizon. But direct evidence grows thin. This uncertainty is where the mystery returns after the triumph of explanation. The microwave background powerfully supports the idea of a hot early universe. It allows cosmologists to estimate age, composition, curvature, and the seeds of structure with impressive success. Yet it also announces a limit. The oldest freely travelling light that can now be seen comes from a universe already hundreds of thousands of years into its history. Earlier epochs must be inferred indirectly: inflation, quantum fluctuations, primordial gravitational waves. These possibilities hover at the edge of evidence, some supported by broad consistency, some still awaiting decisive confirmation. The cosmos therefore offers a remarkable compromise. It reveals its childhood in microwaves, but not its birth in any simple direct way. And so darkness survives one more reinterpretation. It is no longer merely the black between stars, nor only the consequence of finite age and expansion. It is also the visible mask over an invisible afterglow, the sensory face of a universe richer than human eyes can detect. The night sky remains dark, but within that dark there is a nearly uniform sea of ancient radiation, and within that sea there are tiny irregularities that foreshadow every later galaxy. What looks empty turns out to preserve memory. What looks black turns out to glow. What seems silent carries the fossil signal of the first dawn. Yet even this revelation does not complete the story of the void. It only proves that the universe has a history written into empty space itself. The next and perhaps most unsettling chapter begins when astronomers discover that the expansion of the cosmos is not slowing under gravity as expected, but accelerating, as though the emptiness between galaxies contains a hidden pressure or energy of its own. By the late 20th century, the expanding universe has become one of the firmest ideas in cosmology, but it carries an expectation almost everyone shares. Expansion should be slowing down. The logic seems straightforward. Matter fills the cosmos, and matter exerts gravity. Every galaxy pulls on every other galaxy, however faintly across the immense dark. The universe may still be growing larger because of its early momentum, but the collective attraction of all that matter should act as a brake. The expansion rate may not reverse quickly, and perhaps never completely, but it should gradually ease. Space should stretch more reluctantly as time goes on. That is the picture many astronomers bring to their observations. It is not based on sentiment. It is based on everything already learned about gravity, mass, and the large-scale behavior of the cosmos. Then the data begin to turn in the wrong direction. The key evidence comes from a special class of stellar explosions. Type 1 are supernovae. These events are useful because they can serve as standard candles, objects whose true brightness is known well enough that their observed brightness reveals distance. In practice, the method is more careful and refined than that simple phrase suggests, but the underlying idea holds. A certain kind of exploding star becomes a beacon of measurable power. Find such explosions in distant galaxies. Compare how bright they appear, and the depth of the universe begins to yield again. By the 1990s, teams of astronomers use these supernovae to trace how cosmic expansion behaves across time. The expectation is modestly dramatic. The distant universe should reveal an earlier era in which the expansion is faster than now, followed by gradual slowing as gravity does its patient work. Instead, the distant supernovae appear dimmer than expected. Not by a random amount, not in a way easily dismissed as poor calibration or local interference, but systematically, stubbornly. Their light suggests that those ancient galaxies are farther away than a slowing universe would allow. The simplest interpretation is astonishing. The expansion has not been easing under gravity. It has been speeding up. The fabric of space is not only stretching, it is stretching ever more rapidly. This is one of those moments when the universe seems to answer a question with something stranger than the question itself. Expansion is already difficult enough to picture. Accelerating expansion pushes the mind past ordinary metaphor. It implies that the great black reaches between galaxies are not merely increasing, but doing so under the influence of something that acts against gravitational slowing. Space, once understood as curved and dynamic, now appears to possess a large-scale tendency toward ever faster separation. The emptiness between cosmic structures behaves as though it contains a hidden influence, diffuse yet overwhelming, weak in any local sense, and decisive on the scale of the whole universe. The name given to this influence is dark energy, a phrase that clarifies almost nothing, and perhaps that is why it survives. It identifies a mystery without pretending to solve it. Dark does not here mean evil or ominous in any childish sense. It means hidden, unknown, inferred from effects rather than seen directly. Energy suggests a source capable of affecting the expansion of space-time. Yet even these words are provisional. No one has held dark energy in a laboratory. No instrument points to a bottle of it. It is not a substance in the ordinary way. It is a placeholder for whatever drives the observed acceleration of the cosmos. The most conservative possibility is also one of the strangest. Einstein's discarded cosmological constant returns from history with new relevance. What he once adds to his equations to force a static universe may, in a different interpretation, describe an energy built into space itself. Empty space may not be truly empty. It may carry an intrinsic energy density that does not thin away as the universe expands. If that is true, then as ordinary matter becomes more diffuse with cosmic growth, the built-in energy of the vacuum begins to dominate the large-scale dynamics. The void itself pushes. Space expands not merely because of ancient momentum left over from the early universe, but because emptiness possesses its own persistent pressure. That idea has a severe and almost cold elegance. It means the darkest regions of the universe, the broad voids and intergalactic gulfs that seem least substantial, may in the end control the fate of everything. Galaxies shine, stars burn, nebulae form, black holes consume. But the long future belongs to the quiet tendency of empty space to enlarge itself. Matter, for all its drama, becomes secondary. The visible universe is then shaped less by the brilliance of its objects than by the hidden property of the nothing between them. Yet this explanation opens another wound immediately: quantum physics, which describes the microscopic world with unmatched success, already suggests that the vacuum is not a literal blank. In quantum field theory, fields permeate space, and even in their lowest states they are not perfectly still. Fleeting fluctuations appear and vanish. Virtual particles are sometimes invoked as a rough image of this restless background. Though the deeper mathematics is subtler, the vacuum in modern physics is not an absence of all activity. It is more like the minimum state of underlying fields that cannot simply be turned off. If that vacuum energy is identified with the cosmological constant driving expansion, then empty space truly becomes an active ingredient of the universe. But a problem follows that is so extreme it borders on the surreal. Straightforward estimates from quantum theory tend to suggest a vacuum energy vastly larger than the tiny value implied by cosmological observations. The mismatch is enormous. One of the best ideas for what dark energy might be collides with one of the worst numerical disagreements in theoretical physics. This tension gives the mystery a particularly sharp quality. The universe seems to be pointing toward an answer that human theory cannot comfortably absorb. Empty space appears to matter physically, perhaps decisively, and yet the obvious way of calculating its effect yields something wildly wrong. That failure does not make the observed acceleration disappear. It makes it more haunting. The cosmos is behaving as though the vacuum carries just enough energy to dominate on the larger scales, while remaining almost undetectable locally. Why this value? Why not zero? Why not a far greater number that tears structure apart before galaxies can form? Why anything so delicately placed between irrelevance and catastrophe? Some possibilities move beyond a true cosmological constant. Perhaps dark energy is not fixed but evolves slowly over time, driven by a field that fills space and changes as the universe ages. Perhaps gravity itself behaves differently on the larger scales than general relativity predicts in its simplest form. Perhaps the measurements, though now reinforced by many independent lines of evidence, conceal some deeper complexity not yet fully seen. Supernovae provide one path to the conclusion. The cosmic microwave background supports another. The distribution of galaxies and the large-scale web of structure add further support. Again and again the universe seems to say the same thing. Expansion accelerates. The void is not passive, and the consequences are as quiet as they are severe. If acceleration continues, then the observable universe will slowly empty itself, not because galaxies are destroyed all at once, but because more and more of them slip beyond the horizon of possible contact. Light emitted from sufficiently distant galaxies will never overcome the increasing expansion of the space between them. They will fade from view, not by dimming intrinsically, but by being carried into deeper isolation by the growth of the void. The night sky of an unimaginably remote future may belong only to the local gravitationally bound remnants of the present cosmic neighborhood. Everything beyond that may disappear behind an expanding curtain of unreachable distance. The universe will not become less populated in total. It will become less accessible. This is one of the bleakest and strangest implications in modern cosmology. The present era may be unusually rich in visible information. Galaxies beyond the local group are still observable. The microwave background is still measurable. The evidence of cosmic expansion and the hot early universe is still written across the sky. In the very distant future, much of that evidence may vanish from practical view. Observers then, if any exist, might inhabit a cosmos that looks far more isolated and far less revealing than the one known today. The universe may be moving toward a condition in which its own history becomes harder to reconstruct, because expansion has hidden the clues. Empty space would then do more than shape the future. It would erase the visible traces of the past. That possibility deepens the role of the void almost to the point of inversion. At the beginning of the story, emptiness seems like what remains after objects are removed. Then it becomes the dark between stars, the interval that paradoxically survives in a luminous universe. Then it becomes geometry, then expanding spacetime, then the carrier of ancient radiation, then perhaps the repository of vacuum energy. Now it threatens to become the force that isolates every surviving island of matter from the wider cosmos. Nothing, or what appears to be nothing, steadily takes command of the narrative. The more science learns about the universe, the less plausible it becomes to treat emptiness as mere absence. Even the smallest scales seem to echo this unease. Quantum theory refuses a perfectly still vacuum. Cosmology refuses a truly passive void. Black holes raise hard questions about information, horizons, and the structure of space-time under extreme conditions. Inflation, if some version of it is correct, suggests that a peculiar vacuum-like state in the earliest universe may drive an episode of violent expansion long before galaxies form. There is a strange continuity here, though it remains unproven in any final sense. From the earliest fractions of cosmic history to the accelerating future, empty space repeatedly appears not as the leftover stage after physics has done its work, but as a source of conditions that make the work possible at all. This does not mean the mystery is solved by calling nothing something. That would only trade one confusion for another. The point is subtler. The universe seems to resist the old distinction between being and non-being when applied to space. What looks empty has geometry. What looks silent carries radiation. What looks inert expands. What looks like absence may possess energy. The darkness between galaxies is not a simple blank. It is a regime in which the deepest rules of reality announce themselves indirectly by shaping motion, light, structure, and fate. And there the story remains open. Dark energy may be a constant written into space-time from the beginning. It may be the sign of a new physics not yet understood. It may point toward a revision of gravity, a hidden field, a vacuum principle not yet properly grasped, or something more radical than current language can hold. The universe offers evidence but withholds its final grammar. It shows galaxies receding ever faster into blackness. It shows ancient light stretched thin across the sky. It shows matter gathered into luminous webs suspended in depths that seem increasingly powerful the less they contain. In the end, the greatest force in the cosmos may not be a star, a galaxy, or a black hole, but the quiet behavior of empty space itself. And if that is true, then the oldest question returns in a new form. Not what is everything, but what is nothing, and why does it rule so much of what can be seen?